Okay. So I'll start today's lecture. Right. So here is the theorem we want to show since last Wednesday. Okay. And the progress is that we have shown that this function fulfill xm1 and xm2 for a determinant function. Okay? So to reach our goal, to show that this function d is indeed a determinant function for all n terms of matrices, we have to justify that d also fulfill the requirement of xm number 3. All right, so now we continue. Things m1 j a1 alpha r1. Okay, so what is a1 alpha r1? Actually, we replace the first row of matrix A by a multiple of first row. So this is just to multiply the first row of A by a scalar alpha. Okay, so if we do we create the 1j minor of this matrix, and because that when we do the 1j minor, we have to remove the first row, right? And when we remove the first row, then this scaling will be removed. So in this way, m1j is equal to m1ja. Okay. Okay. So you can think about that A1 alpha R1 actually is this matrix. Okay, actually it's this matrix. And when we remove the first row and the just column, so when we remove the first row and the just column, and look at the A here, A R1, R2, Rn. You remove the first row and the just column. You will find that the 1j minors of this matrix is equal to the 1j minor of this matrix. So, okay, so they are equal. Right, so since this is true, so we have so we compute A1 alpha R1. Okay. Right. So we plug the definition of function d. So this is j equal to 1 to n. Okay. And we have alpha A1j minus 1 plus j, determinant of minus 1 of m1j of A1 alpha R1. Okay. This is from the definition of function d. Okay. And the entries of the first row of this matrix is alpha times A1j. Okay. All right, and so we can, so we have a common factor alpha. All right, and then move alpha to here. A1J. But as we have seen here, by using this equality, we have M1J of A. Okay. But this is exactly dA. Okay. So we show that if we multiply the first row of A by alpha, its determinant value becomes to alpha times the value of D at A. Okay, so we have that. And things for 1K M1J AK alpha. Okay. Okay. So AK of alpha RK means that we replace the case row of A by a multiple of alpha of the case row. All right. So the effect is that we do the scaling on the case row of A. Okay. All right, and since the scaling is on case row and k is not equal to k is greater than 1, so if we remove the first row, the scaling is still there. Okay, so that we will see that it's just equivalent to we do the minor, right? So we take the minors of A, but we will replace the k-1 row by alpha k and j. Okay. And remember, it's that the A1, AK1 up to AKJ minus 1, AKJ plus 1 up to AKN. So RKJ is that you just delete the jth component of RK. Okay. So this vector is n minus 1 dimensional row vector. Okay. So the effect, so the 1J minor of this matrix is the same as you first look at the 1J minor of A, and you multiply the k minus 1 row, right, which is just RKJ by alpha. Okay. The reason why it's k minus 1 is because that we have removed the first row already. Okay, so that's why this is k minus 1. Any questions? Do you have any question about this identity? This equality here? Okay. Yeah. Probably. Well. Okay. So this is the case row. Okay. The case row here. So when you remove the first row and the jth column, okay, you get this 1J minor of this matrix. And but A we will move it in here. So that M1J A becomes to R2J RKJ RNJ. Okay, so the 1J minor of A is actually here, so that this row would be K minus 1's row. This is K minus 1's row. Because we already did the first row. So the original case row becomes to the K minus 1's row in this smaller matrix. Okay. And so that M1J A, right, you replace the K minus row by alpha RKJ. Okay. So what is this? This is R2J, and here we have alpha RKJ RNJ K minus 1's row. Okay. Okay. And how about I forgot to put. So the M1J AK alpha RK, okay, becomes to R2J alpha RKJ RNJ. Okay, so look at this one and this one. So you can see that they are equal, right? Because we start with R2J, because we already delete the jth column, right? So that R2J is here, and this one is R. Alpha times RKJ and RNJ here. Okay. So this matrix is same as this matrix. Okay. So we establish this equality here. Okay. So now, so in this case, that K is greater than 1 but less than or equal to K. So the determinant. So we have determinant minus 1 of M1J AK alpha RK. Okay, so the determinant of this matrix, this M minus 1 times M minus 1 matrix, is equal to the determinant of this matrix. Okay, this matrix. But by axiom number 3 of this determinant function, this is equal to alpha, determinant of A. Okay? Because this is the scaling of the k minus 1 0 by alpha. Okay. So that by axiom number 3, so this determinant is alpha times the determinant of this minor. Okay. So look at here. If you look at this one, so the determinant of this matrix, okay, maybe I write here the determinant. Is equal to alpha by axiom number 3, right? So this matrix is just you scale the k minus 1 0 by alpha. So by axiom number 3, you get this one. Okay, so when you look at this one, you will know that you have this idea. So finally, the D of AK alpha RK, this is summation A1J right? So because the scaling is on the k0, k not equal to 1, so that the entries in the first row is still 1A1J here. Okay, and we already know this is alpha times this determinant. So this is alpha summation JA, and again this is alpha times D of A. Oh, I forgot, sorry. Alpha times dA. Okay. So from this one and this one, so if this is 4, this is 5. Okay, so by 4 and 5, axiom number 3 for a determinant function. It's fulfilled by D. Right? So D has x1, xm number 1, xm number 2, and xm number 3. Right? So we conclude that D is a determinant function. Okay, for n times n matrices. And we have done. Okay, so we finished the proof for this lemma. questions? Okay, so now we have the ability to prove the existence and the uniqueness of n by n of determinant functions for n by n matrix. So that is theorem 4.1.2 in the textbook. So the textbook just give you the result without a proof. Okay, so for each n greater than or equal to 2, there is one and only one determinant function on the space of all n times n matrices. Okay, so we will prove this one. By induction on n. Okay, so we'll prove it by induction on n. Now for n equal to 2, okay, there is one and only, so there is one and only one determinant function on 2 by 2 matrices. Okay, as shown in the beginning of this section. Okay, so in the beginning of this section, I have shown that there is one and only one determinant function on 2 by 2 matrices. Okay, and for n equal to 3, there is one and only one determinant function on 3 by 3 matrices. Okay, as shown in example 4.2.2. In my lecture notes, okay, but I haven't discussed that in the class lecture. So, but anyway, I hope you already read through example 4.2.2. Okay, so that for the first two n equal to 2 and equal to 3, the theorem is true. So now we assume, okay, that the theorem is true up to n equal to k, which is greater than or equal to 3. Okay, i.e., there is one and only one determinant function okay, det n on all n by n matrices for each n from 2, 3 up to k. Okay, so suppose we grow one by one. For n equal to 2, we are fine with that. We have one and only one determinant function. And for n equal to 3, we prove the theorem. And now we assume that we have proved the theorem up to n equal to k. In this case, greater than or equal to 3. Okay. So now we let n equal to k plus 1. Okay? So now that n equal to k plus 1. Now, if det if we have a determinant function okay, on k plus 1 times k plus 1 matrices. Okay, so if there is one determinant function on k plus 1 times by k plus 1 matrices A, then by the cofactor, so by the cofactor expansion, okay, using just row 1, okay, by we have okay the det k plus 1 of A is equal to summation j plus from 1 to k plus 1 and the A1j minus 1 plus j and determinant of k and the m1j of A. Okay, so the value of this determinant function on an arbitrary k plus 1 by k plus 1 matrix A can be evaluated by using this unique determinant functions on k by k matrices. Okay, so the value is unique. Okay, so that this value must be equal to this one, and as in these induction steps that this determinant function is unique, so the value is unique. Okay, so since this function is the only determinant on k times k matrices, the determinant k plus 1 function is uniquely determined. And equal to the scalar function dA defined on k plus 1 times k plus 1 matrices. Okay, so whenever we have determinant functions on k plus 1 by k plus 1 matrices, the det sub k plus 1, this function should be equal to this scalar function. Okay, so if we have, then so that they must be unique. Okay, so it must be equal to this scalar function, right? So up to now, suppose there exists one, right? If there exists such a determinant function, then it must be equal to this function. Okay. Now, since we have assumed the existence of determinant function on k minus 1 times k minus 1 matrices and on k times k matrices respectively, right? Then this function, then the function d is a determinant function. On k plus 1 times k plus 1 matrices by lemma 4.2.d. Okay. Because for lemma 4.2.d to be true, we have to assume that we have a determinant function for m minus 2 times m minus 2 matrices. We have a determinant function for m minus 1 times m minus 1 matrix. So that this function defined for all m plus m times m matrices is indeed a determinant function. Okay, so we need the assumption here. But this assumption has been provided here. Okay, so there exists for n from 2, 3 up to k. So in particular, for n equal to k, for n equal to nk minus 1, we have determinant functions. Okay, and because of that, this d function is indeed a determinant functions on k plus 1 times k plus 1 matrices. Okay, so this is indeed a determinant function. And we have just shown that any determinant functions on k plus 1 times k plus 1 matrices must be equal to d. Okay, so this shows that there is one I'm sorry, and only one determinant function on m k plus 1 times k plus 1. Okay, so we have done for the case that n equal to k plus 1. Right? Right, so when we can now use the induction machine, because that when n equal to 2, the same is true for n equal to 2, and it's true for n equal to 3. So now we test for n equal to 4. Okay, but for n equal to 4, we just prove that when n equal to 4, there is one and only one determinant functions for all 4x4 matrices. So the theorem is true for n equal to 4. Now now the theorem is true for n equals 3 and equal to 4. So by induction, the theorem is true for n equal to 5, etc. Alright, so when we start the induction machine, then we will show that. So by induction, there is one and only one determinant function on n by matrices for all n greater than equal to 2. Okay, so we finished the proof here. All right. Okay. So we have finished the most difficult part in this chapter. Okay, and we have a few things to go. All right. So I will mention some of them. Oh, by the way, any questions? No question. Okay. All right. So this is Cramer's rule. Right. So if A x an invertible square matrix, invertible n times n matrix, then the solution to the linear system Ax equal to B is given by, all right, the jth unknown, okay, would be equal to the ratio of two determinants. So it's A sub j B divided by determinant of A. Alright, so we have a new notation. Here we use A sub j instead of A sub I. Okay. So what is A sub j? A sub j is the matrix obtained from A by replacing the jth column. So it's about operations on columns. By replacing jth columns of A with B. Alright, so if A, we know A has n columns. Okay, so that's J N. Okay, and AJ is the jth columns of A. So what is A sub JB? Well, is that, and then the jth column is replaced by B and A here. So here is the jth column. So A sub j, okay, is this matrix. Okay, right, with the same notation. So we let the identity matrix. All right, so we do the same thing. So we replace the jth column of the identity matrix by what? By the unknown vector. Okay, so what is that? This is E1, Ej minus 1, and x here, Ej plus 1, En. Okay? So the jth column in the identity matrix should be a standard unit vector, right? Standard unit vector. So has been replaced by J. So this is this matrix here. Then we have, so that we multiply this matrix. Okay? So we multiply this matrix. This is A, E1, J minus 1, E J plus 1, En. So this is A, E1, A, E J minus 1, AX, A, E J plus 1, A, En. Okay? All right, so we know how to manipulate matrices, the matrix multiplication in chapter 2. So, but what is that? AE1? What is AE1? AE1 is just the first column of A. Okay? See here, AE1, A1, A2 up to N. So A can be expressed as a row vector of columns. Okay? And here is 1, 0. Row vector, column vector. So A1 times 1, A0 times 0, etc. So this is A1. Okay, so this is A1, and this is A, J minus 1. What is that? AX. Well, by our linear system, AX is B here. And this one is A, J plus 1, is AN. So what is this? This is A sub J of B, by definition here. Here. Okay, so A matrix times this matrix is equal to that matrix. Okay, and we take the determinants on both sides, and by applying the product formula of determinant function. So we have okay, so we have this one. But this is equal to determinant function of A, determinant function of okay, together, so that implies that the determinants of X is equal to the ratio okay, so we have this ratio there. Okay, and so now we have to evaluate this one. We don't worry about putting determinant A in the denominator. Why? Because A is invertible. When A is invertible, its determinant is non-zero, right? So there's nothing to worry about, right? When we put determinant A in the denominator here. Okay, so but what is the determinant of this matrix? This matrix should be a simple matrix. So you can see its determinant immediately. So since okay, so you can see that you have x1 and x2 up to xn. Okay, so you have 1 up to here. This is xj. So this is a jth column. This is the jth row. So you have 1 up to 1, 1. And you have all 0, 0, 0 here. Because you just replace the jth row of the identity matrix by the unknown vector x here. So you can do, okay, so by cofactor expansion using row j. Okay, so we do the cofactor expansion using row j here. And in this row j, except the JJ entry, which is xi, all other entries are zeros. Right? So when we do the cofactor expansion, the determinant function, the determinant of this matrix is equal to xj minus 1 j plus j. Okay, and when you so the JJ minor of this matrix, okay, so when you get the and what is that? This is equal to the identity matrix minus 1 minus 1. So this is xj. Because this is 2j, so this is 1. And the determinant of the identity matrix is 1 by axiom number 1. Okay. Right? So this determinant is xj. Right? So finally, so we have the result. Okay. So this is called the Cramer's rule. Okay. We can collect all cofactors of A together into a matrix. So here we have C11. So this is the 1's covector of A. C12A, C1NA, CN1A, CN2A, CNNA. Okay, and we name this matrix as C of A. Okay, so this matrix is called the cofactor matrix of A. Okay, so this is called the. Okay, so we will develop some more results after we take a break now. Okay, for 5 minutes. Okay, I'm sorry. The notation here, because this is a row vector, I can use the parenthesis, because parenthesis in our convention is a column vector. Okay, so I have to use the bracket to represent this is a row vector. Okay, so okay, now the next theorem says that for an n times n matrix A, we have okay, so if we take the product of corresponding components of the ith row of A, so Aij is the entries of the ith row of A. Okay, so say here. Okay, so Aij, you can think about that. You have Ai1. Okay, so this is the ith row, right? Ith row of A, and this is the kth row of A. So you may have so this is the kth row. All right. So now you take the ith row of A, take the kth row of the covector matrix of A, right? And you compute the sum of the product of corresponding components. So Ai1 times ck1a, Ai2 times ck2a, etc. Plus Ain times ckna. So that is this one. Right, and you sum over them, and you will see that the result is either the determinant of A if k is equal to I. So if you select the same row, then this product becomes to the determinant of A. Otherwise, it's 0. Okay, so this formula about the row. And if you do it by columns, so if A, Ij, so you do it for the jth column and the kth column. Okay, so you have the jth column and the kth column. Then again, you have the similar result. If k is equal to j and it's 0, if k not equal to j. Okay, so we deal with about the row operation on rows. Okay, so from theorem 4.2.1 and so theorems 4.2.1 and 4.2.1 prong, we have, so these two theorems is about cofactor expansion, right? Using row, using columns. So using row, we have Aij and the Cij A, which is the determinant of A. So this is the cofactor expansion using row I. And by expansion, according to using column of J, so Aij, Cij is also equal to determinant of A. Okay, so the first two, so this one, and this one, right, are from these two theorems, which are cofactor expansions using row or using column. Okay. So the non-trivial part would be what if we select different rows here or different columns here, so that this sum becomes to 0. Okay. Now we let k not equal to I, and consider the matrix. All right, so consider the matrix which is A, K, I. So now K is not equal to I, but in here we replace the kth row of A by the rth row of I. So you will have okay, so now you see here, when you replace the kth row of A by the ith row, then you have two equal rows in this matrix. So the consequence is that the determinant of this matrix is 0. Okay, so this implies that the determinant of A, K, I equal to 0 by what? By equal row property. Okay, the equal row property of determinants property. Okay. All right. Now we have this one. Right. So immediately we know the so we know this is 0, but by the cofactor expansion, right, using row K of the matrix K I, we have, so determinant of A, K, I, which is equal to summation J equal to 1 to n. Now, because we expand the determinants using the row I, but row I of this matrix, is indeed the ith row of the original matrix A. So the entries here will be A, I, J. Okay? Okay, so in this case, so we have AI1, AI2, AI3, AI4, up to AIN as here. Okay, so we will do that, taking this one. And this is mass 1, K plus J. The determinant of M, K, J of A, K, R, I. Okay, so by the cofactor expansion using rho K. Okay, so even rho K there. All right, and the minors, the Kj minor, you see that this Kj minor, because you will remove the case row. Okay. So when you remove the case row, you will see that this is equal to M Kj of A only. Right? If you look at, compare with A, you remove the case row, the same jet here. So the minus, the Kj minus of A and the Kj minus of AK of Ri will be the same. So these two minus are the same. Okay? Alright, so that we have summation J equal to 1n and Aij. Okay? So this is 1 minus 1 K plus J, determinant of M Kj of A. And by definition, what is that? This is the cofactor of K, the Kj cofactor of A. By definition. Okay, and we just proved this is 0, so this is equal to 0. Okay, so we have finished this part. If k not equal to I, okay, so if k not equal to I, we find that this sum is 0. Okay, now there's one case left here for k not equal to j. So next, k not equal to j, and consider the matrix. All right, so A, K, A, J. AKJ is that you replace the case column of A by its just column. So you have A1, AJ, AJ, AN. This is the the kth column. This is the jth column. Okay, so immediately we know that the determinant, because they have two equal columns, so the determinant of AK, AJ is equal to 0, because of equal column property. Okay, so we have that. Okay. All right, so we do that. So by expansion, now by the cofactor expansion using column K, of AK, AJ. So we have determinant of AK, AJ, I from 1 to n. Now the kth column has entries which is A1j, A2j up to Anj, so it's Aij. Okay, it's Aij minus 1 and I plus k. I plus k because we expand using column k, so I plus k, and the determinant of Mik of AK, AJ. And again, that when you take them, the IK minor, so you remove this column and the ith row, you see that this one is indeed the Mik of A, the same. Right? So the IK minor of this matrix is same as the IK minor of the original matrix A. Okay, when you look at this one. And so you have okay, and so this AIK, and this one is the AI, the cofactor, the IK cofactor of A, and this is 0 again. So we have done complete. Now we can summarize the theorem, this theorem, into matrix equation. Okay, so we observe we multiply A with the transpose of the cofactor matrix. Okay, and so this is A11, A12 up to A1n, A22, A21, A22, A2n up to AN1, AN2, ANn. And when you transpose the cofactor matrix of A, you have C11A, C12A, C1NA. Here is C21A, C22A, up to C2NA, and the CN1A, CN2A, CNNA. Okay? Now, so when you do the multiplication, you will find that this is just the sum of this product is just equal to this case. Okay, for II. Okay, so you get a determinant of A, right? But if you multiply with the other columns, they are all zeros. Okay. Right, so basically when you use this formula, okay. So this is just the second row, right? This column corresponding to the second row of the covector matrix. So the first row and the second row you get 0. The first row with the other row is 0. Now, for the second row of A and the first row of the covector, you have 0. And so you have determinant A. Okay, and 0, 0, and determinant of A. All right, so now you have a diagonal matrix here. And what is that? This is the determinant of A times the identity matrix. Okay. And similarly, when you take the CA, you take the transpose of the covector matrix and multiply A with here. Okay. You will see that after doing so, I think I do not need to. Okay, so this is C11A, CN1A, C1NA, CNNA, and here is A11, A1N, AN1, ANN. Okay, so doing the multiplication just like you are doing the column, because the first row of this matrix is the first row corresponding to the first column of the covector matrix of A. First column, second column, etc. So that you get the same result. And 0. So this is the determinant of A, and multiply with that. Okay, so from these observations that we get a theorem. So we can summarize into the following theorem, 4.2.c, that for any n times n matrix A, we have that A, CA transpose is equal to the determinant of A times the identity matrix, and is equal to CA and T and A. Okay, so we have this identity. So the theorem actually, you can see it's equivalent to the theorem here. Okay, equivalent to the theorem here. But in different way to express it. Okay, this is in terms of matrix equation. Okay, so now the transpose CA transpose of the covector matrix CA of A is called the classical adjoint matrix. The classical adjoint matrix of A, denoted as A dj adjoint of A is equal to the transpose of the cofactor matrix of A. So it's a companion function. And so with that, theorem 4.2.6, so if A is invertible, then its inverse can be written concisely by the formula that is that 1 over the determinant function, the determinant of A times the adjoint of A, the classical adjoint of A here. Okay. So that is the consequence of this result, because if determinant of A if A is invertible, means that determinant of A is non-zero. So you can divide determinant A here, and then you can see that the inverse is actually this formula. Okay, so now you can express the inverse of a matrix by this expressed formula. Okay, but this is expressed formula. Of course, that you have to know how to find the determinant of A, but this is not an easy job to do it. Okay, so actually, at the end of the 19th century, people find this formula. They are so excited, but it has the theoretical value, but not computational value, because to compute the inverse by using determinant function is a huge task. The best way is to use the Gauss-Jordan elimination procedure. Okay, we have learned in chapter 1. That is the most efficient one. Okay, so but it still has the value in theory. Okay, so in some case when we study some nice properties of matrices, sometimes you will use this one. Okay. Okay. All right. So now. I have two more results will be used later, especially in chapter 6. All right, so I want to cover here. All right, together, right? You don't need to divert yourself to this result when we study chapter 6. All right, so now a permutation sigma on the set 1 to n, which is just integers, positive integers from 1 to n. So 1 to n actually consists of the n positive integers. So a permutation sigma on this set is just one-to-one function, okay, from 1n to 1n. Okay, it's one-to-one, then it's bijection, right? Because that this is a finite set to itself, so even though I just say it's one-to-one, but this should be a bijection. Okay. So it's very common, sigma, for example, it's very common to represent a permutation, for example, on on 1, 5, okay, by using these two arrays. So that means that 1 will map to 3, 2 will map to 2, 3 will map to 1, 4 map to 5, 5 map to 4. Right? So this is a kind of permutation of 1, 2, 3, 4, right? So this is a rearrangement of the 5 positive integers. So permutation is just rearrangement of object. Okay? Okay, so a permutation just like this one, and we let Xn be the set of all permutations, okay, on the set 1 to n. All right. So X sub n, so it's called the symmetry group. All right, if you know something of the group, but just say that Sn just the set of all permutations. So you can see that the size. So you can see the size of Xn is n factorial, right? You know that from combinatorial in high school. Right. So the number of possible permutations for n object will be n factorial. Right. Good. So now for each sigma in Sn, we define, okay, the sign of sigma. So Xgn means sign, okay? Sign means +1, -1, okay? So the sign of a permutation sigma is defined to be the determinant of a spatial matrix. Okay? So actually, we permute the n rows of the identity matrix by sigma. All right? So here, consider 5 times 5. So we have 1, all right, so here is E1, E2, E3, E4, E5. If we permute these 5 rows, it means that we permute the B5 according to the sigma, the permutation. Then by permutation, with the sigma, then we end up with, for this one, so the first row will goes to the third row, so this is E3, right? And the second row still second row, that's fine. But the third row becomes to the first row, and this is E5 and then E4. Okay, so you have that. All right, so this is sigma. All right, so if that. Okay, now you can find the determinant of this matrix by row exchanges, right? Because you can go back to the identity matrix by row exchanges, and you count the number of row exchanges. If the number of row exchanges is even number, then the value is 1. If the number of row exchanges is odd, then the determinant value of this matrix is -1. Okay, so that so you can see that the determinant of this matrix, okay, is +1 or -1. Okay, so which is plus 1 over minus 1. That's why it's called a sign. Okay. So every permutation has a specific sign. Okay. Because the determinant value is uniquely defined. We just proved, right? The determinant function is unique. Okay. So for every such matrix, the determinant value is either 1 or minus 1, but should be each one of them. There is no ambiguity. There's no ambiguity, all right? Okay, so this is the sign from them. Okay, so with that, we will have an expansion formula for determinant. It's called the expansion formula for determinants. So we let A be an n times n matrices. Then we have the following expansion about the determinant of A. So it's all right. So we sum over all possible permutations, and each term we have a sign of sigma. All right. So we sum over all permutations. So how many terms do we have? We have n factorial terms. That is a huge number. Consider when n is 100 or 1,000. So it's a huge sum. But the expression is easy. A1 sigma 1, A2 sigma 2, etc. An sigma n. And here we have product of the entries. So from the first row, you select entries according to the permutation. So it's sigma 1, the function value of 1 by this is permutation. And in the second row, you select one entry, right? Right, it's corresponding to sigma 2, etc. Up to here, this is the entry in the nth row, okay? And the entry is n sigma n. And that's it. This is the expansion formula. Very neat. But the computation time is tremendous, huge. Okay? Okay. So we look at the ith row of A. So we know ith row is AI1, AI2 up to AIN. Alright, so be the ith row of A. Alright, so which can be represented. Alright, can be represented as Ri. It's equal to AI1, E1 plus AI2, E2 plus da 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 plus AIN, En. So every row can be represented as a linear combination of the standard unit row vectors, EIs there. Okay, so now by the linearity of the determinant function, of a determinant function on any row. All right, so we have the following result. Okay, so the determinant of A is the determinant of 1, 2 up to Rn. Okay, and now we express the first row by a linear combination of the standard unique row vectors. So it's A11, 1, and this is R2, Rn. Okay. All right, so by linearity, so here we have I1 equal to 1 to n, and the A1, I1, and the determinant of E, I1, R2 up to Rn. So the index is I sub 1. Okay. And again, I sub 1 from 1 to n, A1, I sub 1, and determinant of, so it's E, I1, but now we express the second row by linear combination of the standard unique row vectors. Okay? So again, by linearity, we have I1 from 1 to n, summation I2 from 1 to n, A1, I1, and the A2, I2, and the determinant of E, I1, E, I2 up to Rn. Okay? Now you can do it one by one up to the nth row. So when you go through that, you will have I1 from 1 to n, summation I2 from 1 to n, summation I sub n from 1 to n, and the A1, I1, A2, I2, AN, IN, and determinant of E, I1, E, I2, E, IN here. Okay. Now we look at the determinant of this function. If two indices I1 or I, for example, I1, I2, I1 equal to I2, you have two equal rows, then the determinant will be 0. Okay. All right. So we know that the determinant of EI1, EI2 up to EIN not equal to 0 if and only if I1, I2 up to IN are distinct. If they are distinct, then the determinant is non-zero. Okay? And in this case, we can define the permutation. So we are able to define a permutation sigma in Sn by the following way. Sigma 1 just is equal to I1. Sigma 2 is the I2, etc. up to sigma n is equal to I sub n. So if I1, I2 up to In are distinct, then you can define a permutation like this one. Okay? Okay, so that then determinant of A becomes to summation sigma in Sn, right? So for each combination of I1, I2, In such that they are distinct, you define as permutation. Okay, but the total number of such combination will be all the permutations in Sn. Okay, and there is A1 sigma 1, A2 sigma 2, An sigma n, determinant of E sigma 1, E sigma 2, up to E sigma n. Okay? But by our definition, this is just the sign of the sigma, the permutation sigma. So this is becomes to the SGN of sigma, A1 sigma 1, A2 sigma 2, and sigma n. Okay, so we have done. All right, so this is the expansion formula. Okay. All right, the last result of this chapter to be used later in chapter 6 is about the determinant formula. For black triangular matrices. Okay, right, so we let A, B, C, D, right? Be matrices. All right, and I will denote the dimension here. So A is M times M, B is M times N, C is N times M, D is N times N. Okay, so don't be confused. Okay, A is a square matrix. Okay. M times M. D is a square matrix, N times N. But B and C are in general rectangular matrix when M not equal to N. Okay, so B is M times N and C is N times M. Okay. All right, so then we have now the determinant of lower triangular. So we have A, C, and 0, D. All right. So this is lower triangular. Okay. Now look at the dimension M times M. This is N times M. So this zero matrix, it's M times N, and this is N times N. Okay. So that the matrix, this is M plus M times M plus M matrix. Okay? So this is a very big matrix. All right? This lower triangle, right? So it's the black lower triangle matrix. Black lower triangle matrix. Its determinant function can be computed as it's the product of the determinant of A times the determinant of D. So it's the determinant of A multiplied with determinant of D. Okay, and also it's equal to A, B, 0, and D. And again, M times M m times n times n, so this is n times m. Okay, so from here you can see that if you change the C matrix arbitrarily, right? You change the C matrix, any entries in C, it will not affect the determinant value. Similarly, if you change the entries of B in any way, you will not change the determinant value. Okay, so this is a very nice formula for Bloch triangle matrix. We have two types of Bloch triangle matrix. This is the Bloch low triangle. This is Bloch upper triangle. Okay. Okay, so we will consider the Bloch lower triangular matrix A 0 and the CD first. Okay. Right, so there are two cases to consider. Okay, so we consider two cases. Case 1, A is non-invertible, right? A is non-invertible. Okay, so A is non-invertible here by the invertible matrix theorem in chapter 3. Okay, the m rows of A form a linearly dependent set. Okay, so when A is non-invertible, then A has m rows. These m rows form a linearly dependent set. Now, if the row of A form linearly dependent set, then we extend zeros here. So this implies that the m rows of the m times m plus m times m plus n matrix A and the 0. Right? So we look at this matrix here. Then these m rows also form a linearly dependent set. Right? Obviously, because we just append zeros at the end of each row vectors. So if the m rows of A are linearly dependent, means that there exists a linear relation on the m rows. Okay, but this linear relation will be immediately extend to the linear relation of the m rows of this bigger matrix, because here they are all these entries are all zeros. Okay, all right. So now we have m rows which are linearly dependent. In this case, so that so that the m plus n rows. Now, since the m rows are linearly dependent, so when we include the raised n rows there, then this matrix has the m plus n rows of this matrix of the m plus n times m plus n matrix. A, 0, CD also form a linearly dependent set. Okay? Because a small number of rows already linearly dependent, then when you add more rows, then the bigger set is still linearly dependent. Okay, so now the m plus 1 rows of this big matrix form a linearly dependent set. So again, by the invertible matrix theorem, okay, this matrix is non-invertible. Okay? So what we have shown is that if A is non-invertible, then this big matrix is also non-invertible. Okay? And then, so determinant of A, 0, CD, which is 0, and 0 times the determinant of D, okay? And 0 is the determinant of A, and this is determinant of D. Okay, so we have done. For the first case, when A is non-invertible. So when A is non-invertible, we establish that the determinant of this low triangle matrix is equal to the product of the determinants of A and determinants of D. Okay, right. So that is the first case. How about the second case? Okay, so the case 2, A is invertible. Okay, all right. So things, right? So now the reduced echelon form of A is identity matrix by the invertible matrix theorem. Okay? Right? So there exists a sequence, right? E1, E2, Ek of M times M elementary matrices, okay, such that by applying this elementary matrix on A, you get the reduced echelon form. So this is E, K, E2, E1, and A. Okay, so you have this one, and then by the product formula, okay, so we have 1 equal to the determinant of identity matrix is equal to the determinant of Ek, determinant of E2 times determinant of E1 times determinant of A. Okay, so this is equal 1. Alright, and now by applying the same corresponding sequence of elementary row operations on the submatrix A and then 0. Okay? Right, so because that the reduced echelon form is obtained by applying elementary row operation on rows of A, right? So that is this one. And then we apply the same row operations on this matrix. Okay? So that we turn this matrix A 0 CD to identity and the CD. Okay? So we can turn them. So A will turn to the identity matrix, but CD remain there. Okay? We just keep CD intact. Okay, we don't touch them. All right, and so what we have done? Well, we reach to this matrix by row operation. Okay, by using EK 0 0 EK 0 0 E2 and the E1 0 on the matrix A. Okay. All right. So actually we apply. So the corresponding elementary matrices in this bigger matrix is this one. Okay. So okay, now since EI and this bigger matrix EI 0, these two correspond to the same elementary row operations. Okay, so they will have the same, so that determinant of EI will be equal to the determinant of EI 0 okay, so this is by XM to XM3 and Theorem 4.1.1. This is for the replacement row operation. This is for scaling, and this is for the row exchange. Okay, so they will have the same determinant value. Okay, so that they will have the same determinant value. All right, so that when we take the determinant, the I m times m 0 m times n and the CD will equal to determinant of EK. So this determinant is equal to determinant EK up to determinant of E2, determinant of E1, and the determinant of A0 CD. This is M times N. Okay, so we have this one. Now, this is the identity matrix, right? So that each column has 1. We can use the pivot to cancel all the entries in C. Right? So using the replacement row operation, all the entries in C can be cancelled. Okay, so things can be reduced to and the 0 and the D. Okay? By replacement row operations. Okay? So that every entries here can be cancelled by the 1, right? So that we can do the forward elimination to eliminate all the non-zero entries in C. Okay, so we will turn the C to 0 into there. All right, by replacement operation. So that the determinant of this matrix, of this one, CD, becomes to the determinant of identity. Zero. Okay? Now, this matrix determinant of is equal to 1, 1, 1, and the D okay. So you can reduce the order, right? This one by apply, remember, this one is determinant of M. Okay, remember that. For special type of the determinant of this matrix, this determinant is equal to determinant of M. Okay, so that this is equal to, we reduce the size. Okay, and keep doing that, you get the determinant of D. Okay, so this is by repeatedly applying theorem 4.2.a. So this is a theorem 4.2.a, right? So whenever we can move the matrix into this pipe, then the determinant of this matrix is equal to determinant of M only. So this is identity. So we have 1 there. So every time we reduce one one order of the determinant. So finally we get the determinant D. Is that okay? So we just repeat it using the same theorem again and again and again. By how many times? Actually, m times. Because this is m times m matrices. Actually, m times. All right. So finally, we have determinant of D. All right. So this is determinant D. Rotated, right? This is determinant of D. Determinant of D is equal to determinant of EK, determinant of E2, determinant of E1, and the determinant of ACD0. Okay, so we have that. This is 2. All right, so we have 1 there and 2 here. Now we divide 2 by 1. Okay, so we have determinant of D divided by 1, which is equal to determinant of EK, determinant of E2, determinant of E1, and the determinant of A. And here, determinant of A0 CD, and this is determinant of EK, determinant of E2, and the determinant of E1, and determinant of A. We are not afraid of putting determinant A here. Why? Because this is non-zero, since A is invertible. So you can cancel them, and the final result is here. A0 CD is equal to the determinant of A and the determinant of D. Okay, and we're done. Okay, so I have kept to use the results that we have shown before. Right, so this is for the lower triangular cases. How about upper triangular cases? Well, that would be easy. Finally, for block upper triangular matrix A, B, 0, D. This is n times m. We have, okay, so determinant A, B, 0, D. Okay, n times m. All right. The determinant of a function of a matrix is the determinant of its transpose. Transpose there. So this is the determinant of. So the transpose of upper triangle matrix becomes a lower triangular. So this becomes AT, BT, 0, and the DT. And this is 0. This is n times m. Becomes m times n. Alright, so now we have a lower triangle. But we have just shown the lower triangular matrix, we have the result. So this is determinant of A transpose, determinant of D transpose, okay? But once again, determinant of A transpose is equal to determinant of A, determinant of D transpose is equal to determinant D, and we have done. Okay, so finish the proof. Alright, so the upper triangle part will be easy once we done the lower triangle part. Okay, we're done. Okay, so right, so I finished chapter 4 finally. A long journey on the determinant function. Well, so I try my best to put almost every fundamental properties of determinant functions. So in your future of the career, if you need a property of determinant function, you can look back to chapter 4, and you will find that all the essential material will be inside in chapter 4. Right. Okay. So that's it, and I'll see you next week.